Okay, today I hope to get through three ideas. One is to finish off some of the material on asymmetric information. The next bit is to introduce the idea of repeated games. With asymmetric information, we're going to talk about educational screening, which is a little different from the signaling idea that we did yesterday with used car warranties. And then we're going to look at what's called moral hazard and incentive contracting. Now, I realized after yesterday's class that the diagrams we've been using can get kind of complex. And sometimes there's some algebra and some equations. You wonder, what's going on? I thought we weren't really doing math in this course. Well, what I want you to do is take from the text descriptions, the little diagrams we have, some of these equations, the ability to tell a story. Okay. So yesterday, the story was about adverse selection, the lemons market. And there's some intuition there about used cars. There's good used cars, bad used cars. Bad ones are called lemons. Good ones are called plums or cream puffs. So you kind of simplify things down. And what you're doing is you're thinking, oh, the people who have lemons know that they're lemons, and the people who have cream puffs know that they're cream puffs, but the people who are buying them don't know that. So that's the asymmetric information. We're kind of looking at the PDIP structure of this game. And then we played around a little bit with an equilibrium idea where when you thought about it for intelligent, rational people, at the end of the day, which is in the equilibrium, people will believe that the only kind of used cars in the markets are lemons, and that's the price they'll be willing to pay. And the only used cars that'll actually be sold will be lemons. The cream puff car owners won't be able to sell their products, even though there's some willing buyers out there. The problem is the willing buyers don't know what the quality is of the car. They can't observe it. They know that the other guys can, and the only sustainable equilibrium is that adverse selection one, which is the problem, the lemons problem. So then we said, well, how can we get around this problem, this bad equilibrium, where there's lots of willing buyers for cream puffs who like to pay more, but they're not willing to pay more for lemons? Well, we thought of two ways. One is a certification idea, and we briefly looked at that, but certification costs. Then we looked at a warranty idea, and we wrote some inequalities down. We'll see some more inequalities today. And again, you just kind of put them in your head. You realize, oh, there's a left-hand side and a right-hand side, and it's really the best response reasoning that we've been using all the way along. Before we were comparing, was 4 a higher number than 3? We're getting our best response. Well, here we're looking at this left-hand side of an inequality and the right-hand side. Which one is higher or lower? And that's really best response reasoning. Now, that reasoning is in these models is called, or these theories are called incentive compatibility constraints. Okay, so there's some new language you're going to learn here. We've got adverse selection, we've got signaling and screening. We have these inequalities, which we call incentive compatibility constraints, and basically they're just best response ideas. Okay, people, when they're interacting strategically, they're making their best response, that is their own choices in light of what they believe, what the uncertainties are, and what they believe other players will do. What we saw with this warranty example was there was a length of warranty, in this case this little model that just turned out to be 5 months, where the used car buyers couldn't see the quality of the car, but they could look at a car that's bundled with a 5-month warranty and a car that doesn't have any warranty, and they could quite reliably infer that the car with the warranty is the cream puff, and so they're willing to pay high, and the car without the warranty is a lemon, so they're willing to pay low. Now, that was an idea of a strategy that separated out the various types in the market on the supply side. And the types are the things that the buyer doesn't know. The initiative for that new equilibrium, which we called a separating equilibrium, came from the people with the used cars, and particularly the cream puff guys who can't sell in the lemons market realize, I'd like to get my car sold, so I'm going to offer a warranty. So when the initiative comes from the informed party, we say that's a signal. The one we're going to look at today, the educational screening, a screen is where the uninformed party tries to figure out what truthful information is that they don't know, and they're going to set up a screen. Just generally, you can think of them as signaling strategies or screening strategies, but technically the difference is who takes the initiative, who moves first in the game. So let's have a Let's have a look at this educational screening example that's in Dixon and Skeeth, and ours, we're just going to follow along from what the text does. Up here on the left is this PDIP, okay? This is always what we bring to these strategic interaction situations. Who are the players? What can they do? What's their information? And what are their payoffs? We start off with employers and employees. And the employees, there are two types of employees. There's employees with a high ability, and there's employees with low ability, which we will say they're challenged. So C for challenged, A for able. The employers, the blue guys, they value ability and are willing to pay, say, $150K a year. We live in hope. And the challenge guys, they'd be willing to hire these challenged people if they could identify them. They just don't want to pay them quite as much. Okay, what can the employees do? Well, the employees can take some education. Okay, and I put down here X as the number of tough courses. And you know yourself, like in the university, there's kind of soft courses and there's tough courses. I mean, you know that there are some soft courses, and you know there's some really tough courses. Okay, so here we're going to look at the choices that the employees can make of some tough courses. And when you're doing a tough course, even a person who's kind of challenged, if you work your butt off, you might be able to get through the course. But you know that there are these people who have the great skills, the able people, and they can get through the course as well, but they can do it with less personal cost. What we're going to do is put down a cost per course for the able people and a cost per course for the challenged people. Now, by this, we don't mean you both pay the same fees. It's just that, let's face it, you know, when you're trying to pass a course, the dollar expenditure, you know, $500 a course or whatever it is one thing, but it's the time and effort that you put into it that is the real cost. And so here we're going to distinguish between the two types. One has a low cost of completing a tough course, and one has a high cost. Let's go back to the employers. The employers don't observe, they can't tell from just looking at an employee whether you're an able type or a challenge type. What they can see is how many tough courses you took, okay? So what we're going to do is think of the payoffs to each of these players as their net wage. The wage from the employee standpoint is a benefit, but the wage from the employer standpoint is a cost. And for the employees, they'll get paid a wage, and they'll subtract off the total cost they have to do to earn that wage. The employers will pay a wage and they'll have some valuation. Now we're going to assume that, well, we've got the valuations up here, we're going to assume that the wage that's actually paid is the employer's value, okay? It would always be something a little bit less, otherwise the employers wouldn't hire anybody. But let's just imagine, just keep things simple, that they have to pay their valuation, okay? Now what are the strategies? What can they do? Well, the strategies are you can take a set of courses. We're going to try and figure out what this X has to be, a set of tough courses. And for the employers, they're going to have what we call a trigger strategy or a cutoff strategy. And the employer's strategy is this, okay? If I see the number of courses you take is greater than some number N, then I'm going to regard that person as a high quality type, an able type, pay them $150. Okay, so if you like, the employers are putting out this wage schedule, which say, you know, if you get a BA or you get an MA or you get a PhD, we'll pay you so much. So it's a sliding kind of scale depending on how many tough courses that you take. This is the structure of the game. It's a two-player game. There's employees and there's employers. What can they do? Well, they can decide to take courses or not, and the employers can decide to hire or not. What's the information? Well, there's this asymmetric information is that the employees know their own type, which is their ability. The employers don't see that type. But they can see, everybody can observe how many courses, tough courses you actually took. Again, what we're going to do is, like in the warranty case, we're going to try and think about, is there some way that you could set up this educational screen so that the able types took the tough courses and the challenge type didn't take the tough courses. So they would self-select into those two groups. And if that happens, if we can separate out the types, we can use their actions. Did you take the course, tough courses, or did you not take the tough courses, to reveal their type? So that's the idea of this screen. We can discover what the private information is, not by asking them, but by setting up this educational screen. Okay? And the reason that we don't ask is that words are cheap. Anybody can say that they're abled. Few would say that they're challenged. But are you willing to back up what you say by taking these tough courses or not? Let's look at the perspective from the challenge types. What we're looking for is some kind of a separating equilibria, and in that separating equilibria, what we'd like to have is the challenge types decide not to take the tough courses, and that would reveal that they are the challenge types. If the employers are willing to pay $100K for a challenge type, okay, then on the left-hand side here, this is the wage that the challenge types can get if they don't take any tough courses. On the right-hand side is that they sort of think, well, look, if I take the tough courses, I get through this degree, it's going to be hard work, but I'm going to get the higher wage. I'm going to get 150. So on the right-hand side, we put the 150, which is their wage, minus the cost of them taking the course. Now, what we've set up here is that each course is like an equivalent dollar cost of $9,000, $9K. So we're subtracting off 9 times whatever n is. If n is 1 course, that's going to be 150 minus 9. If it's 2 courses, it'll be 150 minus 18. If it's 3 courses, it'll be 150 minus 27. If we can make n big enough, then this right-hand side will be smaller than that left-hand side. So that's what we're going to try and do. Let's look at it from the perspective of the able types. Okay. We would like the able types to take the n courses. So we want them to be willing to take the $150,000 a year wage, subtract off the cost of doing that degree, getting those tough courses, which is 6 times n, and we want that left-hand side to be bigger than the right-hand side, which is the wage they would get if they didn't take the courses. Now, these two relationships, which are really best responses, right? What we're saying is we would like for the able type to make a best response to take the courses, and for the less able type to not take the courses. You know, I'm willing to hire both. We just want to pay them different wages. And we call these, again, incentive compatibility constraints. It's just that logic of the best response reasoning, only here we're kind of thinking it as a design problem, right? It's a game, and we're trying to think, how could we design this game, this educational screening game, so that we could separate out the market, so that these two types would do different things? Well, if you play around with these inequalities, you can come up with a relationship that says, look, to satisfy these two inequalities, we have to have n less than or equal to 8 and greater than or equal to 6. Okay, so let's take the bottom end, n equals 6. 9 times 6 is 54, so 150 minus 54 is going to be less than 100. So that'll make the challenge types prefer not to take the tough courses. They'll get employed at the lower wage because they don't take any courses of 100K. What about when n equals 6 here? Well, 150 minus 36, that's 114. That's greater than 100. That works. Okay, so if we make the number of tough courses big enough, like 6, 2 wouldn't be enough, right? If we made n equals 2, only 2 tough courses, then the A types would prefer to have a salary that is 150 minus 18. Of course, the C types would prefer a salary of 150 minus 18 if n is equal to 2. But if n is equal to 2, the A types will prefer to take the tough courses, but so will the challenge type. We don't separate them out. So we've got to have n big enough, but we can't have n too big, because if n is too large, then the A types will think, oh, I don't want to do this PhD. It's like, this is too tough. Okay? So they won't do the tough courses. Neither will the challenge do the tough courses. And in those two situations, we might get a pooling equilibrium. Okay? But here we're trying to concentrate on the idea of a separating equilibrium. Yeah, we can get a separation of the types, so the types reveal their actions. Employers are willing to pay 150 for someone who does a course 6 units, and 100 for someone who does none. Okay. When they're willing to pay that, the red types will self-select into those two categories. One will take the courses, the other won't. They reveal their types, and so the employer's beliefs will be confirmed. Okay, they'll find that, oh, gee, if I offer this kind of wage, I do get an able type, and if I offer that kind of wage, I'm going to get a challenge type. Okay, so that an educational screen can separate out the market. Just like in the warranties case, the warranty signal was able to screen out the market. Now, there's a little twist to this, though. Okay, in setting up this game, there's something I didn't mention at the beginning, which I do want to mention now, is that the education, the number of tough courses that you take, does not affect your productivity. Okay. What we thought about here was the able types could go to work, and employers, if they knew those able types, effective of their education, I mean, in terms of tough courses, would be willing to pay $150K. And same for the challenge types. They'd be willing to pay $100K. It doesn't matter how much education they have. The education doesn't affect the employer's valuations of their productivity. The education of the employees doesn't affect their productivity. It just costs to do this education. And this is a bit of a problem. Here what's happening is, in order to separate out the market, to get the truth revealed, the able types have to take the 6 courses, which is costing them $36K. Okay. The challenge types don't pay that educational cost. The only benefit out of this is that the market separates itself out. The truth is revealed, but it costs. It'd be quite nice if you could sort of think of, is there some way of, like in the warranty case, is there some way of certifying this an able person and certifying it a challenged person? Then they're going to go ahead and get their wages, but we don't have to spend all this money on education, which is totally unproductive in this model. Now, I'm not saying that your degrees are totally unproductive, but I do think they perform a signaling function for employers, and it costs you guys a lot to create that signal which separates your abilities out from people who are unwilling to do the university education. And take another step is you get your undergraduate degree, you could go a little farther. You could get an honors degree, or you can get an MA degree, or you can get a PhD. And I understand, like in Germany, a PhD isn't big enough. You have to have this extra degree on top of it. Okay, and you wonder, is that really improving people's productivity? It might, and it probably does. But it also could be just performing a signaling function for employers to be able to screen out able people from unable people. Okay. So that's the idea of educational signaling. It's a solution to the adverse selection problem, which is otherwise people are just going to pool, and employers would pay an average wage. The able types would think, well, it depends what their supply price is. They don't want to work at that wage, and employers can only get less able. Now, I want to introduce another concept called moral hazard. Before I do this, I'm going to show you this neat little photograph. This photograph is of Skipper's Canyon. I don't know if you've ever been to Skipper's Canyon. It's down by Cornet Peak. And as you go up to Cornet Peak, you can turn left and you can go up to Shotover River, which is really majestic, but the road is the road from hell. It is just terrible. The road here, you can see this bridge. It's the Skipper's Canyon Bridge. There's a cemetery at the other end of it and a little campground. The two are correlated, I guess. Because if you make it to the end, you feel like dying. The road is very narrow and treacherous. It winds its way all the way up along here. I put a little bullet point as to actually where the road goes. It's an impossible road to drive on. The first time I drove on it, I had my own car. I was with my kids. We'd gone skiing. We thought, we're just going to go up here and check it out for a day. And it was a nightmare. The road is very narrow. It's slippery. If it's wet, you're slipping all over the place, and you see these enormous cliffs which you could slide down on. Okay, I was in my own car. If you try to rent a car in Queenstown, you won't be given insurance if you go onto the Skipper's Canyon Road. And the reason is that it's such a treacherous road, it doesn't really matter how careful you are or not careful as a driver. The insurance companies don't trust you to take care of their car on that road. Okay? This is the problem of moral hazard. The term actually originated in the insurance industry. I put up kind of just a general characterization for you, but you sort of think of moral hazard as a problem in a relationship where one party can't observe what the other party does, or they can't observe what it is that you know. So you might be a consultant, and you've got some specialized knowledge, some specialized information. The person who's hiring you doesn't have that specialized knowledge, that specialized information. So they have to rely on you to tell them stuff, okay, to search things out for you. I think I told you the story about this x-ray that I had with my back problem, is that the consultant took this 1.5-year-old x-ray. He didn't take a fresh x-ray to look on it, so the advice he gave me was lousy advice. I didn't know that because I didn't know that he wasn't making the effort to look at fresh results. Okay. Similarly, with this hidden action thing, is the insurance company is offering you this automobile insurance on a rental car or even on your own car. They don't know whether you're going to take care of it or not. And that's what's called a moral hazard problem. Now, the term moral hazard doesn't mean it's immoral. It just means it's kind of costly for you. You're in your rental car, you're out driving, and it's maybe it's a fast rental car, or maybe it's an old tank, and so you're not going to take care of it as well as you would if it was your own car. That's what we call a moral hazard problem. And it's not that you're necessarily a bad guy. It's just that there's some effort cost for you to really take care of something else that belongs to somebody else. So when we're thinking about moral hazard, you want to look at a situation of strategic interaction. Usually we think of a two-player game. People can take various courses of action, but the information is asymmetric. One party can't see what the other party does or what the other party knows. Usually we want a difference in their incentives or interests. Okay, so if everybody had the same preferences, the same interests, it wouldn't be a moral hazard problem. But so we're going to have some diversity in people's interests. And the key thing is this difference in information, which usually comes because it's very difficult to observe or measure things. So let's have a look at a simple little two-player game. On the handout, I put out 3 little graphs of this, so we're going to build this idea up. This is a game between an employer and an employee, or you could think of it as an owner and a manager. And the basic idea is that the employee can put in a high level of effort or a low level of effort. So over here, the employee, who's often called the agent here, the agent could put in a high level effort or a low level effort. And then some things happen. You're working hard, it's a wet day, you're getting out to by other people. All these kind of events are going to affect whether you're going to succeed or fail. And so we're going to have a move for nature here where you can either succeed, which is up here, should have an S on it, or it can fail. Then your employer will decide to pay you something or not. I put a little fan on the right-hand side here because there's all different levels of payment that they could actually make. But we haven't quite got the information structure here, or the uncertainty in this game. It turns out that we're going to put 2 information sets around these nodes where the employer is making payment. And notice how these 2 nodes are connected together. They're saying, okay, if it's a success, going up along here, which should have an S on it, then the employer can't distinguish whether that success came from a high effort on the employee's part or a low effort. Okay? You put in a high effort, could turn out good, could turn out bad. You put in low effort, it could turn out good, it could turn out bad. All the employer can see is the outcome was good. Didn't know if you put in high effort or no effort. Okay. Similarly down here, the project could fail, or the task could fail. Did it fail with high effort, or did it fail with low effort? The employer can't distinguish. It can distinguish between a success, going up here, and a failure. Now, meanwhile, the employer has to decide whether to pay you or not. Okay. So what I've done here is I put up a general kind of scheme of possible payoffs, and it works something like this. This is the kind of game that we've had before. There's some actions, nature takes some actions, employer makes some payments, and out over here, there's some payoffs. So let's look at these possible payoffs. Let's imagine that the employer pays a salary S. So there's an S here, an S there, an S there, and an S there. No matter what happens, and no matter what your effort, the employer pays a salary S. Got that idea? So the key thing here is a salary doesn't depend on whether you got a higher effort or a low effort. B is a bonus. And the bonus, now what might be nice is you might like to say, well, gee, if you work really hard, I will pay you the bonus. Okay? Not just if the whole thing succeeds will I pay you the bonus, but if you work really hard. But for the employer to do that, they have to be able to observe whether you put in high effort or low effort. And they can't do that, okay? They might observe the time you spend on the job, but they can't observe how much effort and intelligence, enthusiasm, or whatever. Or they might be able to suspect whether there's intelligence, enthusiasm, or whatever, but if asked to write it down in a contract, it would be too subjective to ever do that, okay? So we're saying, okay, you have to pay, if you want to pay a bonus, you pay it if the project succeeds, going out along here, but you don't pay the bonus if the project fails. So that's the idea of a bonus. Remember, the salary is paid irrespective of your behavior or whether it's success or failure, but the bonus is paid if the project is a success, okay, if it turns out. What about this number 50? Well, what we've done here is we said if you put in high effort, it's going to cost you. Okay? A low effort doesn't actually cost anything, but in this situation, if the red player puts in a high effort and there's a failure, they get their salary, and we take off 50 for this. It's just a deduction for a cost of effort. If they put in a high effort and a success, they get their salary and the bonus, and they have to pay this high cost. The distinguishing things here in this cell and in that cell is when they're putting in low effort, they don't, it might be a failure, but they get their salary. They don't have to put in the extra effort. If they put in low effort and success, they get their salary and the bonus, but they don't have to subtract out the extra effort. What does the extra effort do? Well, the extra effort affects the probability of success. So in this game, we're thinking we don't know whether the project's going to be successful or not. There are lots of outside things that can happen. If the employee works pretty hard, using our language from before, we'd say the probability of success, given they work hard, we're going to put as 0.8. Okay, we're just going to use the number 0.8, but it's going to stand for that uncertainty about whether it's going to be a success or not, and that's going to depend upon the employee's effort, high or low. If it's low, the probability is 0.6. If they put in high effort, it's 0.8. So this is the structure of the game. We've got who the players are, what they can do, what their information is, and what their payoffs are. The information structure of the game is that there's some uncertainty. We don't know what nature's going to do. The employee doesn't know it. The employer doesn't know it. But they both believe that, okay, if the guy works hard, there's a good chance, 80%, of the project succeeding. And if you don't work hard, it's a low chance. So that's an inherent kind of uncertainty. It could be, hard work, it fails. Okay? It could be no effort, and it succeeds. Okay? And all those other four possibilities. Let's just go back and look at the payoffs to the employer. The number 600 is like if the project succeeds, so it's a success, that's their total revenue. Okay, they got to pay then your salary and your bonus if it's a success, but if it's a failure, they get nothing and they still have to pay your salary. Okay. So here, from the employer's standpoint, they're bearing a lot of risk, right? They've got high revenues if the thing succeeds, but no revenues if it fails. And meanwhile, if it fails, they don't have to pay your bonus, but they do have to pay your salary. Okay, so this is a game of this kind of imperfect information. There's uncertainty, and there's asymmetry as well, because the employee knows whether they're going to work hard or not, but the employer can't see it. So that captures all of the basic features of these games of asymmetric information. And what we're going to do is look at the problem from the standpoint of the employer and the standpoint of the employee. There's a language in these understanding of these games that instead of thinking of the insurance company and the person renting the car, instead of thinking of the employer and employee, instead of thinking of the owner and a manager, we talk about the principal who's going to be doing the payment, and the agent who's going to be doing the work. So it's called a principal-agent game. It's a two-player game of imperfect information.
Now, in this problem, the employee is sometimes called the agent, and the employer is sometimes called the principal. The reason for that is this general 2-by-2 problem where there's some moral hazard is characteristic of a number of situations: employees, employers, rental car companies, and the drivers, owners of businesses or equipment, and operators, managers. The basic idea is the agent is the one who can put in higher, low, or variable effort choices, and the principal is the one who makes the payment to the agent, designs a contract, pays them compensation, but can't observe what the effort levels are for the agent. So I've put the game in the upper left-hand corner here, and let's look at the idea first from the agent's perspective if he gets a small bonus. So down in the right-hand corner over here, I have a diagram of expected payoffs for the agent under various scenarios. Now, this is the basic expected payoff diagram we had from mixed strategies, and we used in the venture capital games, or we use anywhere where there's some uncertainty. So let's have a look and see how the payoffs here map into the payoffs in this diagram? Well, the first thing is, on this axis we have the probability of success. So this is the beliefs by either one of the players, but in this case the agent, about the chances of success. Could range from 0 up to 100%, and we know from the specification of the game that the chances of success are 0.6 with a low effort and 0.8 with a high effort. The line displays all the possible beliefs, and then there's several that we're interested in. The endpoints where it's definitely a failure and definitely a success, and then these intermediate points where everyone believes the chances of success at low effort is 0.6 and chance of success at high effort of 0.8. So first concentrate on this purple line. The purple line takes the low effort compensation. First, if it's a failure and we're at low effort, then you get your salary. So that S comes over here to this S. If it's a low effort and a success, then you get your salary plus the bonus. That translates over to this point over here. So these endpoints are the payoffs you'd get if it was a success and if it is a failure. And the difference between them is the bonus. Now, we've made it kind of a relatively flat line, so the difference between this height and that height is very much. It's a small bonus. Now let's look at the expected payoffs for a high effort level. Well, if you have a high effort level and it fails, then you only get your salary and it's cost you 50. So this point S minus 50 corresponds to that S minus 50 there. 50 being the cost of providing the effort. If it's a high effort and succeed, you get your salary plus the bonus minus 50, and that translates over to this point over here. So again, we get the two endpoints on a line. We draw the straight line between them, and that straight line between them reflects the expected payoffs for high effort, depending on what the probability of success is. Over here, if the probability of success is very low, then the expected payoffs are over here. If the probability of success is very high, the expected payoffs are there. Okay. So the red line, that is high effort, brings lower payoffs than low effort does. You get the bonus irrespective of whether there's low effort or high effort, and you get your salary irrespective of whether there's low effort or high effort, and there isn't much to choose between them. Now these are just lines of possible expected payoffs. What we might think about is the actual expected payoffs under the beliefs that we've specified. Now with low effort of 0.6, we know that there's a 60% chance of getting this point and a 60% chance of getting that point. So it's 60% away along the line. That height there is the expected payoff to the agent if he puts in low effort and has a corresponding 60% chance of success. What about high effort? Well, with high effort, you could get lower payoffs generally, but a higher chance of success. With an 80% chance of getting this point and a 20% chance of getting that point, so we're 80% along this line. And if you notice, the height here is lower than the height there. That means if you're looking at best responses, given the beliefs, that low effort has a higher expected payoff than high effort does, with a small bonus. What if we make the bonus larger? Well, let's give it a try and have a look. Well, to make the bonus larger basically tilts these curves up. It keeps the same distance between them because that's the cost of effort, but it tilts these curves up. So if you exert low effort, you get your salary in case of a failure, that is probably a success, is 0, so it's a certainty you're going to failure. Then your expected payoff is S. If it's a success, your expected payoff is a salary plus bonus, which is now pretty big. And then with the probability 0.6, which is the chances of success given you've put in low effort, the expected payoff is a height there. We do the corresponding calculations for the new high effort expected payoff lines. Okay, again, salary minus cost of effort into failure, salary plus big bonus minus cost of effort into success, and probability weighted average at 0.8 gives an expected payoff along here, which is now higher than the expected payoff with a low effort. So again, we're comparing the expected payoffs with a large bonus for low effort and high effort from the agent standpoint, and with a large bonus, then even though a bonus system is risky, the agent would prefer to put in the high effort rather than the low effort. Now, we call this relationship an incentive compatibility constraint. What we want is the expected payoff, which is the probability weighted average of these two endpoints along this red line, to be more than the expected payoff, which is another probability weighted average along the purple line. Okay, so this one we want to be greater than that one, and that's what we call an incentive compatibility constraint. You can write these things down algebraically, essentially, and the algebraic expressions of these pictures lie up along here. So we call these incentive compatibility constraints. For the high effort, the agent's payoff is essentially the salary minus the cost of effort plus probability of success times the bonus, so it's like the expected bonus. And under low effort, it's the salary, but there's no cost of effort here, or no extra cost of effort, times the lower probability, 0.6, times the bonus, the expected bonus. So these are payoffs from high effort, payoffs from low effort. We want this one to be higher than that one. We can rewrite the constraints, and we find that the bonus has to be greater than or equal to 250. So we need a big enough bonus to actually satisfy this incentive compatibility constraint. Okay, just to be clear, the high effort expected payoff is along that graph, but it has that algebraic representation. The low effort expected payoff is along this graph and has this algebraic representation. For this guy to be bigger than that guy, we take this thing here and make it bigger than that, do some rearranging, and we come out with the bonus has to be greater than or equal to 250 to be able to motivate the worker to put in a large enough effort. Now, there is one other consideration we have to worry about here in this game, and that's where we've got a branch at the beginning that the agent has an opportunity to work elsewhere, and the outside wage we're assuming is. So we also have to make sure that the salary plus bonus, the expected payoff, is bigger than 100. So we put a little line over here at the outside option height of 100, and we call this a participation constraint. Again, we want the red dot to be above the black line, so that geometry is translated into that algebra over here. Here's the expected payoff for high effort. It has to be greater than or equal to the outside option salary they have. Do some rearranging, and we find that if the bonus is equal to 250, then the salary can actually be greater than or equal to minus 50. What's a minus 50? Well, a minus 50 is a negative salary. That means the guy pays you, the employee pays you 50 no matter what the outcome is, for the opportunity to get hold of this big bonus at 250. Now, it may be difficult to collect a negative wage, so let's put a social constraint as that salary has to be greater than or equal to 0. So essentially now we have a situation where if the salary is equal to 0 and the bonus is greater than 250 or greater, then the employee would want to work rather than not, so that's this decision here. So along those nodes, and given that they want to work, they'll want to put in high effort rather than low effort as long as this bonus is greater than 250. Okay, so that's the expected payoffs for the agent where there's a salary plus bonus contract, or an incentive contract. Let's look at the problem from the agent's perspective. This is where I came a cropper in class a little bit, and that was partly because the labeling of my diagrams just threw me off. So, we're looking at the expected payoffs for the principal under a bonus contract where we can get the guy to work and we can get him to put in the high effort. Alternatively, we can just pay him a salary equal to his outside wage and give him no bonus. So the question we want to ask is the salary and bonus contract worth it? And to figure that out, what we have to look at is the expected payoffs to the principal, which will depend on whether the project's a success or failure, and which will mean that he will either earn 600 and have to pay his bonus and his salary, or earn nothing and have to pay his salary. So the entrepreneur has a risky option here. We're looking at the expected profit with that bonus and salary. as compared to just offering the guy a flat salary and no bonus at all. And the lowest flat salary we can get away with is 100. Now it turns out if you crunch out these expected payoffs and these formulas, the expected payoff up here is $280 or $280,000, and the expected payoff down there is $260,000. But rather than do the algebra, let's work with our little diagrams. Okay, again, the employer has some beliefs along this axis and some payoffs along this axis. Over on this side are the payoffs if it's a failure, and over here are the payoffs if it's a success. Now remember, we have to pay the bonus of $250 and the salary of $0, and we get the revenues of $600. So this height up here would be $350. Down here, if the project's a failure, then we don't have to pay any bonus and we don't have any salary that we have to pay, so the profits are going to be 0. And along the line will be the expected profits, which will vary according to the probability of success. Now, with high effort, the probability of success is 0.8, and so the probability weighted average of 0.8 on 350 and 0.2 on 0 is 280. Let's do the low effort situation. Now, we're just going to get low effort if we pay him a basic salary of 100. In that case, we'll get revenues of 600 minus 100, which is 500. And if we don't earn any revenues because it's a failure, we'll have to pay him a salary of minus 100. The expected payoff, it's either going to be up here at 500 or it's going to be down here at minus 100. But a probability 0.6 on 500 and a probability 0.4 on minus 400 gives us an expected payoff of 260. Let's put that other guy back in there with a high expected payoff. And you can see here that the expected payoff inducing high effort, which is the salary plus bonus contract, or expected payoff with low effort, which is the basic salary with no bonus, the minimum salary we can give them but no bonus, that it is worth it. Okay, for the principal, it is worth it to design an incentive contract and to pay it. There are other scenarios where when you're making this comparison, it's just too expensive to offer a bonus contract, so it'll actually be better to just pay a salary and no bonus, even though you're not inducing the high effort. The high effort isn't worth the extra cost. So that sums up our discussion of models of asymmetric information. We've had several kinds of models here. We had the adverse selection material, venture capitalist material, with signaling and screening as ways of getting around the adverse selection problems, which for us meant that you could get at the truth, possibly, through these separating equilibria, but to get at the truth is costly. There's going to be someone's going to have to make a resource cost, or there's going to be some lost opportunities or lost benefit in order to do this signaling, which signals the truth, or the screening, which screens the truth. Then when we look at the moral hazard problem, the moral hazard problem is an issue. We'd like to induce higher effort, and strategically with the flat salary it's better for an employee just to put in low effort. We can induce high effort with a bonus payment and design an appropriate contract which will make it an equilibrium for the agent to put in high effort rather than low effort and to keep working here, and the principal to earn a higher expected profit from inducing that higher effort through a bonus payment rather than straight salary. Again, we can have other situations where in the moral hazard problem it isn't worth the cost to induce the extra effort. Okay, the bonus payment would have to be too high from the employer's standpoint to make it worthwhile from actually to induce the higher effort. It's better just sticking with the lower effort. So it isn't always efficient for the agent or the principal to induce higher effort. It just depends upon what the costs of effort are relative to the expected benefits. Okay, so now we're going to move on to introduce the finite repeated games as we discuss in class here.
So we're going to move on to a slightly different topic, which is called repeated games. Now, if you remember the 6 questions, one of the 6 questions was, is the game repeated or not? And it turns out strategies in repeated games are quite different than in one-shot kind of games. So what I've put up here is a simple 2x2 simultaneous game. Red player, the blue player. Blue player has 3 actions. Red player has 2 actions. These are the payoffs. Don't try and put anything practical or realistic on this. It's just a simple simultaneous game. And it has 2 Nash equilibria, here at A and Z, and here at B and Y. Okay, and we work out the Nash equilibria using our best response kind of reasoning. What we want to do is repeat this game. Now, when I say repeat, we're going to take the entire game and literally run the identical game after the first game. So what we call the first game is the first stage game. When we move to the second stage, it'll depend upon what happened in the first stage. Okay. So what I've done here is said, well, supposing they play A and X in the first stage of the game, then we'd bring a branch out this way here. If they play A and Y in the first stage, another branch. If we play A and Z, another branch. And similarly on the bottom down here. So if we're going to draw the full game tree, which we don't want to do because it gets too complicated, okay, is that in the first stage there'll be a branch leading from every combination of choices in the first to some combination of choices in the second. Supposing the second stage is one where they've played, red players played A in the first round and the blue players played Z in the second round, then we're going to play this game again. Okay. If you notice, the payoffs here aren't the same as the payoffs up here, and that's because in these repeated games, what we do is we think of, when you're repeating a game, the final payoffs are a combination or a total of the earlier payoffs. Now, here we're going to just take simple sums of these totals. So every one of these numbers down here is a red 1 and a blue 4 more than the corresponding sums up there. And that's because in the first round, if they play A and Z, the payoffs are 1 and 4, so that's where the 1 and 4 is. Then we play the game again. Well, if they play A and X, they're going to add 1 and a 4 here. If they play A and Y, they're going to add a 1 and a 4 there. If they play A and Z, they're going to add a 1 and a 4 there, etc., etc., etc. Okay? So the items in this entry here are all of the sums of 1 and 4 to each of these cells up here. And you'd have to get the final payoffs for each of these branches, we'd have to do the same thing. Okay? When you add up all of the combinations of things in the first round and things in the second round, you can get all of these possible black dots out here. Okay? So here are the red payoffs, here are the blue payoffs, and let's say if we take down here, we take a 0 and 0, which are the B and X in the first round, and we take a 4 and a 3 in the second round, then we're going to get a 4 and a 3, so that corresponds to that black dot there. If we take 4 and a 3 in the first round, and we add on this entire matrix up here, we get an 8 and a 6. So over here we have an 8 and a 6. We can have a 5 and a 7. We got a 5 and a 7 up over there. So these black dots are just looking at the aggregate total of payoffs. Again, to trace the thing through, draw the entire game tree, it's going to take a lot of effort and computation-wise to get things right. But if you look at this graph, you can say, oh, these are the total payoffs out here, right? Notice there's some along here which are a lot higher than the ones down there. It turns out that the Nash equilibrium we'll look in this game can be either of these triangles in terms of payoffs or in that square. And that's what we're going to do at the beginning of the next class, is come through and analyze how to look at a repeated game, figure out what the Nash equilibrium in the repeated game are, and you might have some intuition that says, oh, if we just play a Nash equilibrium in every one of the stage games, then we should be able to get a Nash equilibrium in the overall game. And that's true. Okay? So just remember that idea. Here's a Nash equilibrium here. There's a Nash equilibrium there. We could play this Nash equilibrium in the first round, that Nash equilibrium in the second round, and we get a 3 and a 5. So that's like a 3 and a 5. And oh yeah, that is a Nash equilibrium. Okay? So you can put together combinations of these stage game Nash equilibria to have a Nash equilibrium in the overall game. But you can also get some other really interesting ideas in these repeated games where we can get to this point out here where you get pretty high payoffs for everybody, and this point here is associated by playing A and X in the first round. Now A gives the red player the highest payoff they can get, 4, in the first round, and in return in the second round, the blue player gets the highest payoff they can get. Okay, so if you get a chance to have a look at that, there's an explanation in Watson about how to think of this finitely repeated games. And the basic idea is we want to use cooperation in earlier rounds with rewards and punishments in later rounds. Okay, that's for today.